Okay, as I said, I won't be here tomorrow, but I'm bringing you tomorrow's lesson today. That's why I have the same clothes on. However, I did make a mistake, so I don't know if my AP kids are watching. If I did, Emily, I owe you a tick mark. I think that's about number 7, the 7th time I've been wrong this semester. But I said we were going to cover not potential energy, that's what we are going to cover. I said we were going to cover conservation of energy and power. Well, somehow in my whole discussion of kinetic energy this morning, I forgot we had to do potential energy. So today's lesson is actually on potential energy. So if you want to pause the video right now and get out the PowerPoint and pull it up, we are on the slide that says 5.4 potential energy. So potential energy, it says in the notes, may be thought of as stored energy or stored work, I should say, stored work, such as in a compressed spring or maybe a stretched spring, or an object at some height above the ground. So that's two types of potential energy, that's stored in a compressed or stretched object, and then the potential energy stored in an object that is some height above the ground. Work also changes the potential energy of an object. Let me give you a simple example of that. If I had, let's say, your physics book. Let's say this physics book was, I don't know, a little over 1 kilogram. And I were to set it on the floor and I were to lift it 1 meter above the floor. So I applied a force to it through a displacement. And once again, what's force acting through a displacement? That's right, it's work. So I did some net work in lifting the book. Let's say it was 25 joules. So I did 25 joules of work in lifting the book 1 meter above the floor. Well, guess how much potential energy I just stored? That's right, 25 joules. I stored 25 joules of potential energy. So that last statement that says that work done on an object also changes the potential energy of an object. That object went from having no potential energy on the floor to having 25 joules of potential energy when I did 25 joules of work on it. So that's how work and potential energy are related. We talked about in the lesson this morning how work and kinetic energy are related, but for an object to gain potential energy, work has to be put into the system or into the object itself. So there's two types of potential energy we're going to cover. The first is called elastic potential energy. Elastic potential energy is like a spring, as I said, or something that is stretchy, like a rubber band. Think of a trampoline spring that doesn't stretch too well, or think of a slinky that's very easy to stretch, or even springs or things that compress, like a ballpoint pen. When you press down on a ballpoint pen, you're actually compressing a spring in there. So you're storing potential energy in that spring when you compress it. The formula for elastic potential energy is this. The abbreviation for potential energy is a U. P is reserved for power, so P doesn't work for potential energy. So I like to call it U with a little E subscript that refers to elastic potential energy. So the formula is 1/2 kx squared. So those of you that are in AP Physics, we've already covered what the spring force is. The spring force was kx. So the amount of force needed to compress or stretch a spring was k times x. But the potential energy stored in that spring or spring system is 1/2 kx squared. Now, we do need to define what the variables are. So what two things determine how much energy is stored in something that's elastic? Let's see if you can come up with those. Okay, one is how stretchy is the material. different materials are made out of different substances, and that's what K defines. K is referred to as the spring constant. The spring constant is a variable, a number that represents how much force is needed to stretch or compress the material per meter. So actually the unit for spring constant is a Newton per meter. It's the number of newtons needed to compress that object per meter. So think of a slinky, like I said. A slinky would have a very small spring constant because it does not take a lot of force to stretch a slinky. However, a trampoline spring would have a pretty high spring constant. It takes a lot of force to stretch a trampoline spring. The springs in trucks, like the struts or the coilover springs in the suspension, it takes, you have to have a jack to jack up those springs to be able to put them in there. So that's a very high spring constant. So that number varies. It'll vary for even rubber bands, for example. Not all rubber bands have the same spring constant. A little thin rubber band would be fairly easy to stretch, and you shoot it at somebody and it probably wouldn't hurt too bad. But if you get a real thick rubber band, it takes a lot of force to pull it back through a displacement. But if it takes more work to pull it back, then it must store more potential energy. So you shoot somebody with that one, and it's going to leave a stinging mark on them if you shoot them with that one. So that's called the spring constant. It's either given in a problem, or if you have everything else, you could figure it out. Well, what is X? X is the distance that you either stretch or compress the material. So it's the distance you stretch or compress whatever is elastic. I just happen to have an example here with props here at home. I have a bow. If you know anything about archery, not all bows are the same. This one is a compound bow, but usually I would pull a bow back the same distance every time. So if I'm pulling it back, I would pull it back from this, a resting position, to this, I stored some potential energy, so I applied a force through a displacement, so that's probably not going to change, but X does change, K does change in different bows. Different bows have what they call a draw weight. This one, I don't know what it's set on. It's fairly easy for me to pull back, so it's probably a 60 or so draw weight, somewhere around there. An 80-pound draw weight, I probably couldn't pull it back. It would be kind of hard for me to pull that one back. So what this does is it goes from relaxed position. I have to do some work on it. I have to apply force through a displacement, and I just gained potential energy when I did so. This system here, this elastic material, gained potential energy, gained elastic potential energy. And the cool thing is, if there was an arrow in there, when I let go of it, all of that potential energy would be converted into kinetic energy of the arrow. And the more energy I store in it, the more kinetic energy that arrow is going to have when it comes out. Provided I don't lose any energy to the environment, which I probably will. I told you we would get the conservation of energy, but that's a great example of elastic potential energy, one that's stored in a bow when you shoot an arrow. I just happen to be a Walking Dead fan, and if you watch The Walking Dead, Daryl, he shoots a crossbow, and you rarely see Daryl pull back the crossbow that he shoots. I think I've seen one episode where his kind of cocks like this when he cocks it, but crossbows have an extremely large spring constant in them, much larger than a bow that you draw back with your hands. And most crossbows have to have, you put your foot in it, and you have two hooks that hook around the string, and you pull it back to cock it back. and it takes a lot of force to do that. So crossbows convert a lot of potential energy to kinetic energy when it shoots. They're called bolts instead of arrows, when it shoots a bolt out. So that's elastic potential energy. So think of your cars and your car engines, anything that's mechanical, that needs a spring or something to store elastic potential energy in it. That's a good example there. The other type of energy that's potential that has to do with the motion of objects or the conversion of potential to kinetic energy is gravitational potential energy. Gravitational potential energy has to do with how high an object is above some defined zero level. Now we're going to define the ground as our zero level. So anything above the ground is gonna increase in gravitational potential energy. So this one's pretty easy. This is gravitational potential energy. U with a little sub g, gravitational, is equal to mass times gravity times height. Gravity is acceleration, which of course is negative 9.81. So really you're just taking the weight of the object, mass in kilograms times 9.81, which is how we found weight in every other problem we've done with forces, and multiplying it by the height. So the example of my book, if that book was, I said it was a little over 2 kilograms. Actually, I was probably wrong. I meant 1 kilogram. It's probably a 1 kilogram book. So 1 kilogram times 9.81 times height really gives me 9.81 newtons, not 25 joules. I mean, joules is what I said. By the way, the units here for both of these are joules, just like in kinetic energy. Any energy is measured in joules. So mass times gravity times height. Let's do that again. Let's say the book is 1 kilogram, which is about 2.2 pounds. I think that's what I was thinking in my head is a book is about 2 pounds, and I said 2 kilograms. 1 kilogram times 9.81 meters per second squared times 1 meter. So that would be 9.81 joules. So let me go back and correct. Dang it, Emily, I made another mistake. Let me go back and do that again. If I lifted a 1 kilogram book 1 meter above the ground, I just stored 9.81 joules of potential energy. So I also did 9.81 joules of work to do that. So I did work to store energy. And when I let go of it, if I were to let go of it, when we talk about conservation of energy, as it falls, it's going to be losing potential energy because the height gets lower and lower and lower. But as a result, because it's accelerating as it falls, it's gaining velocity. And remember, kinetic energy was 1/2 mv squared. So it's going to be gaining kinetic energy as it falls. So it's going to be losing potential energy as it goes down to the ground, but it's going to be gaining kinetic energy. So that's your conservation of energy there. That's kind of a little heads up of where we're going with this. I did put a little lab at the end of your daily agenda tomorrow on Friday the 20th. I put it as optional. If you can get your hands on maybe a golf ball or a tennis ball or a baseball or something like that. Basically, it's dropping a ball from 1 meter, determining the gravitational potential energy of that ball before it's released, and then finding the kinetic energy of the ball when it hits the ground. If you used a golf ball is about 45 grams, which would be 0.045 kilograms. So if you did 0.045 kilograms times 9.81 times 1 meter, that would tell you how much potential energy it starts with. And then you could find out how much kinetic energy it had when it hit the ground. The lab basically walks you through step by step exactly what to do. I know you don't have a balance at home, a digital balance like I do in the classroom, but any kind of ball, you could probably Google what is the mass of a golf ball, or what's the mass of a baseball, or what's the mass of a tennis ball. and get a good estimate of a mass that you can put in there. But be sure to convert that to kilograms when you're using this formula. So it's an optional lab. You can do it if you want to. I'm not going to make you do it, since you may or may not have the materials at home to do that. But I thought it'd be a fun thing to do, those of you that did. And there's some questions at the end of it that relate to gravitational and kinetic energy, gravitational potential and kinetic energy. There's nothing about spring potential energy in that lab, but just know that in order for an object to have mechanical energy, which is what we're going to talk about on Monday, mechanical energy could be kinetic energy. If something is moving, it has mechanical energy. It could be spring potential energy. Mechanical energy involves that, or it could have gravitational potential energy. It could involve that. So these three things, elastic, gravitational, and kinetic energy, all make up your mechanical energy. So if you remember that poster that I have in my room that has all the equations on it, it has mechanical equations, and that involves this. Now, are there other types of potential energy? Absolutely. Chemical potential energy is one, but chemical potential energy is not mechanics. That's what you learn about in chemistry. It would take an input of energy to release that chemical potential energy. For example, in nuclear fission reactions, you're releasing a lot of chemical potential energy. In gasoline has, actually that'd be nuclear energy, wouldn't it? We'll use gasoline for example. Gasoline has a lot of chemical potential energy in those bonds. Octane is the molecule. And in order to release that chemical potential energy, you have to combust it. You have to add an energy source to it. You have to burn it, and that chemical potential energy is released. So only when you do that is that energy released. So the main two sources of potential energy when it comes to mechanics, classic mechanics in physics, are elastic and gravitational. So hopefully that makes sense to you. You won't see me again until Monday when we do cover power and we cover conservation of energy. I hope I got it right this time, or else I'm gonna have another tick mark because I'm wrong. But I think that's got you caught up through Friday the 20th, and I'll see you guys Monday. Have a great weekend.